So now that we've developed phasors, we are now in a position to start to think about series RLC circuits. So before we run straight into that, let's just draw one for reference here. There we go. So my first pause and ponder question for you is, what physical quantity is the same for all of the circuit elements? Okay, so I hope we can agree that we have since this is in series, the current is the same everywhere. So this means that at any particular time, all of the circuit elements will be sharing the same current phasor. So we can go ahead and let's just draw the phasor diagram for the instant when the current phasor happens to be crossing the x-axis. So I'll go ahead and draw our current phasor here in purple. So that's the current phasor, and I'm just calling it I because it's the same for all the elements. And then we can go ahead and draw our voltage phasors. So this would be the voltage phasor for the resistor. And then we remember Eli, the Iceman. In an inductor, the voltage leads the current. So that means it'll be 90 degrees in front of the current. And then finally, ice. Let's draw the capacitance phasor like that. They'll be 90 degrees behind the current. And keep in mind, the whole assemblage of phasors will be rotating counterclockwise with the angular frequency omega, but I think this is probably the most useful moment to look at. So to find the voltage, the applied voltage phasor, what's associated with our EMF, we know that by Kirchhoff's loop law, the voltage here would have to be equal to the sum of the voltages here. And the beauty of the phasor technique is we can just go ahead and add the phasors as if they were vectors. So let me just redraw that down here real quick. So again, I'll just draw in the current phasor pointing straight right, just so we have a point of reference. And we'll just go ahead and add them up. So I'll use, if you're adding like vectors, I'm going to go ahead and say use the tail to head rule. That's probably the most useful here. VR, VC, and then let me choose a different color here. That will make this our EMF phasor. And the angle that the EMF phasor makes with respect to the current, this is our phase constant, phi. So this is the minus phi that we saw before when we were writing the equation for the current. Okay. So how do we go about relating the applied EMF to the current going through the circuit? Well, from that point, what we can do is, again, look at the phasor diagram. This EMF phasor here is the hypotenuse of a triangle, so I can say E squared, whose y-axis, whose y dimension here, this much right here, is going to be equal to VL minus VC. So by the Pythagorean theorem, we'll say VL minus VC squared, that's the y bit. Then we'll say plus VR squared, that's the x bit. Now from our definitions of inductance, this is equal to IXL. That's equal to IXC. and this is equal to IR by Ohm's law. And those are all squared. All right. So we can pull I squareds out of everything and take the square root of both sides and get that the EMF is equal to I times the square root of XL minus XC squared plus R squared. Sorry, that should be a plus right there. This quantity here inside the square root, we call that the impedance. Because remember, this is describing how the resistor resists the flow of current. This describes how the inductor and the capacitor react to the current. So put it all together, resist, react. Okay, someone went through the thesaurus and found impede. So that's capital Z, and it's defined to be the square root of XL minus XC squared plus R squared. So then this is the R-like quantity for the whole circuit. It's not a resistance, only that much is the resistance, but this whole thing sets the scale of the current. So we can write that the EMF is equal to IZ for the circuit. And again, the units of impedance here, well, this is ohms, that's ohms. It's all ohms. And similarly, we can go through and look at our phase angle here and realize that this will be the arctangent of the Y piece over the X piece. So you can say that the phase angle is the arctangent of VL minus VC over VR. This will be IXL minus IXC over IR. And we can have cancel Palooza with the I's. So we get that our phase angle is the arctangent of XL minus XC over R. So what does this mean here? Well, it means that the EMF will be the biggest when XL is equal to XC, because there's nothing we can do about R. But XL and XC, if they're equal to each other, will cancel. And so then the impedance would just be equal to the resistance. If XL and XC are unequal, then there will be a difference, which we square, and then the impedance will be greater, which means for the same applied EMF, you'll get less current. In fact, this is enough of an issue that the cosine of this angle actually gets a name. It gets called the power factor. And I'm sure in electrical engineering texts it has a symbol, but I'm not aware of any symbol for it in physics. We usually just say the power factor, cosine phi. And the point here is that, remember, the only thing that dissipates energy is the resistor. So the voltage across the resistor will be equal to the applied EMF, then going back here, times the cosine of phi. So if we go ahead and plot out current as a function of the frequency we drive the circuit at, let's mark this as the resonant frequency. You'll see the same kind of quality factor things that we saw before with mechanical simple harmonic oscillators. With the higher quality factors, relating to lower resistances. So say that this is a low resistance and that's a high resistance, and then the one I drew in between is somewhere in between. So what is this frequency? Turns out it's the natural driving frequency, because the impedance will be as low as it can be when XL equals XC. So if we just say, all right, let's let XL equal XC at resonance, this is omega naught L. This is 1 over omega naught C. So rearrange, we get that our resonant frequency is 1 over root LC, as we saw before. So if you drive the circuit at the frequency it naturally wants to oscillate at, that is where you're going to have the most current going through the for a given applied EMF. Now, this deal is a big enough. This is a big enough deal to the power company that they actually do things to encourage industrial consumers to keep their power factors as close to 1 or the phase angles as close to 0 as possible. Because here's the thing, is that the power company wants to minimize the current that they deliver. So if you have the impedance being greater than the resistance, let me rephrase that. The power company wants to deliver as much current to dissipative loads as possible. If we have an impedance, if we have the inductive and capacitive reactances mismatched, this is going to increase the impedance, which is going to decrease the current for a given EMF. So that just literally means fewer customers that they can supply. So the power company wants to maximize the current they can deliver, and so they actually bill the industrial users on basically the integral of the current that goes into the company times the voltage. So this is they're getting billed for the energy they would have used if they had, and if their phase angle was 0. If their phase angle isn't 0, well then what will wind up happening is the company will be drawing more current than they need to, which is a waste to the power company. So by billing them as if the phase angle was 0, that creates an economic incentive for factories to get their inductive and capacitive reactances equal. Now, why would they ever be unequal in the first place? Well, remember, a factory is basically just nothing but a bunch of motors. I know I'm greatly oversimplifying here, but there are an awful lot of motors in factories. And motors are just giant windings of wire. So you've got lots and lots, so they're giant inductors. So you have lots and lots of inductive reactance. So what they are doing is they are encouraging the factory to put in giant banks of capacitors to get the capacitive reactance of the factory to match the inductive reactance of the factory. And by doing that, dropping the impedance of the factory as low as possible. Alrighty. So let's just try this one. Let's say that for a certain RLC circuit, we had a resonant frequency of 200 kilohertz. We then double the capacitance. What happens to the new resonant frequency? Well, we remember that our resonant frequency, our angular frequency, is 1 over root LC. So this will be 2 pi f naught equals 1 over root LC. So this is again an example of a scaling problem. We want to know what happens if we've changed something. So usually what you do is just write the same thing twice and divide. So 2 pi times the new frequency will equal 1 over root. Since the inductance doesn't change, we leave it the same, times the new capacitance. And we divide that by 2 pi times our old resonant frequency. And divide that by what that is, 1 over root L times our old capacitance there. All right, cancel, 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 cancel. Clean it up, it's C over C prime. All right, so our new frequency will equal our old frequency times root C over C prime. And we were told that C prime was 2C, so cancel, cancel. So it will be 200 kilohertz times 1 over square root of a half, which is 0.707. So this is going to be 141 kilohertz. Now there's some other applications of this without the inductor. If you've ever looked at your stereo, you know that usually the speakers come in sets with collections of speakers of different sizes. This is because remember that sound waves are most efficiently made by speakers that are roughly on the same size as the sound wave. Well, since the range of human hearing can vary from 20 to 20,000 hertz, it means correspondingly the sound wavelengths will vary by a factor of 1,000 as well. So it's pretty much impossible to make a single speaker that can very efficiently generate all the wavelengths. So you usually do 2, 3, 4, depending on the design of the speaker. So what you'll do is you'll design a crossover. So your stereo source here will be providing AC electric that's heading off to the speaker. And let's say this is going to the subwoofer. What they'll often do is somewhere in the amplifier cabinet, they'll have an RC circuit like this, and then they will send these leads here off to the speaker. And turns out that what this will do, this is going to the subwoofer, so actually let me say off to the subwoofer. So this is our low frequencies are going through here. So this gets called a low pass filter because that's what passes through. Now, say you want to send something off to the tweeter, you just do it the other way around. So you just actually go off, put another couple of taps across the resistor. So then this is the bit here that's going off to the tweeter. So our high frequencies here. So if you plot this out, so we're just plotting both the voltage across the resistor and the voltage across the capacitor here. Our low-pass filter, let me just label that right there. Our low-pass filter will fall off something like this. And then our high-pass filter, which is what this is, will go up something like that, approaching the EMF. All right, and if I were a better artist, this point would have lined up, so I'm just going to draw in a dotted line. This is called the crossover frequency. You can show, but I won't here, that this is equal to just 1 over RC without the root. Or without any roots or anything like that. Now, the question that I have for you here before we finish this off is, if you take a look at this, this is drawn reasonably accurately. You can see that the voltage is higher than half of the EMF. And for the low pass filter, so this is what's coming off the capacitor here. And for the bit that's coming off the resistor, again at the crossover frequency, it's higher than half. So it seems like if you add the two of these together, that's going to be bigger than the EMF that the stereo is providing. So why is this not a problem? Pause and get back with me. Okay. It's not a problem because the capacitor hits its peak 90 degrees out of sync with when the resistor hits its peak. So although these are, we're plotting what the RMS values are here, we don't, our instantaneous values being 90 degrees out of phase will still always obey Kirchhoff's loop law here. Alrighty. So in the next series of videos, we are going to transition to optics. So catch you over there.